Hello again. So last time we left off with the cardinality of rationals. So before we move on, just want to summarize that we found that the cardinality of naturals and the cardinality of wholes and the cardinality of integers and rationals, though I didn't demonstrate how, are all Aleph null, the same level of infinity, which means all four sets are equivalent to each other. They're all the same size. Now we're going to talk about the next infinite sets, which is irrationals. Now rationals are things like rad2, rad3, pi. But they all have something in common, and that is if they're written in decimal form, such as this, and they don't have a pattern and go on forever, that is a special distinction characteristic of an irrational number that other real numbers don't have. So I'm going to try to prove that you cannot put irrationals into one-to-one correspondence with the naturals. So I'm claiming that irrationals don't have one-to-one correspondence with naturals. And if they don't, then they're not equivalent with naturals. These are all equivalent with naturals because these are all countable. Countable, remember that we can list them without skipping any and match them up with the naturals. So I'm claiming that these are not countable or not listable. And this time I'm going to prove it. So here's my hypothesis. If a subset of irrationals is uncountable, then irrationals, the set, all of them, are uncountable because they have a portion that's uncountable. So I'm just going to prove that this small subset of irrationals is uncountable, and that should be enough to prove that irrationals are uncountable. Okay, so the small set I'm going to use is, the subset I'm going to use is all irrationals between 0 and 1. That's my subset. Okay, so I'm going to list just the first 5 or 6 irrational between 0 and 1 in no particular order. So these are just random irrational numbers between 0 and 1. So they all have to start with 0 point something, of course. And I'll just do one more. Okay, there we go. So I'm going to put dot, dot, dot here because there are many more irrationals between 0 and 1. So these are all the irrationals between 0 and 1, dot, 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 because it's impossible to list them all, but assume that this is all of them. Now, I'm going to now write over here in this box, I'm going to create an irrational that is not in the list that you see on the left here. Okay, so I'm going to repeat that. All the irrationals between 0 and 1 are here. But I'm claiming that I'm about to create an irrational that isn't there, and I can prove that it isn't there after I write it down. Okay, so here it is. Okay, for the moment, let's not worry about the dot, dot, dot here or the dot, dot, dot here. I can prove that this 5-digit decimal number, sorry, I think there should be 6 digits, hold on. No, 5-digit decimal number is not in this list. So I can ask you simple questions to prove that. Could this number be the first number in the list? No, because the easiest way to prove that is the first digit 6 is different from the first digit 5. Could this number be the second number in the list? No. I could compare the first digits, but I could also compare the second digits. This 1 is different from the 0. The third digit is different from the third digit in the third number. The fourth digit is different from the fourth digit in the fourth number, and the fifth digit is different from the fifth digit in the fifth number. Now, if I had listed more numbers here, I would have ensured that the digits that follow were different from every single number that followed here. And the way I did that is I took the first digit in the first number and increased it by 1 just to make sure it's different. Then I took the second digit in the second number, increased it by 1 to make sure it was different. Then I took the third digit in the third number, increased it, made it a 0 to make sure it's different. So just the first 3 digits, I knew it couldn't be the same as the first 3 numbers because I changed an important digit in each number to create this new number. And I continue to do that. I changed this one in the first number, then this, then this, then this, then this. And if I had written more numbers, I would have done the same thing. I would have continued to change these digits in the number. Always ensuring that there's at least one digit that is different in my number than any number in the list. So this shatters my hypothesis, which was I can list all irrationals between 0 and 1. Remember, I said first that that's what I did here. But I just created a number that isn't in this list that supposedly contains all the numbers between 0 and 1. Which means anytime I can shatter that theory that this is possible. So I must conclude that it's impossible to list all the rationals between any two numbers that you pick, because I can always create one that isn't there. So if I can't list the irrationals between 0 and 1, they must be uncountable. And if this set of irrationals is uncountable, then all irrationals, the whole family of irrationals, are uncountable. If the whole family of irrationals is uncountable, then you can't list them. And if you can't list them, you can't put them into 1-1 correspondence with the naturals, therefore not equivalent. And if they're not equivalent with the naturals, guess what? They're not equivalent with wholes, integers, rationals, any countable set. So their cardinality can't be our friend Aleph No. It must be a different cardinality. And that cardinality is more than Aleph No. I emphasize that, more than Aleph No, an infinite number. Okay, that's hard to fathom. How can there be something more than an infinite number? Well, don't think of this mystery number as a number. Think of it as a level. Whatever the cardinality of irrationals is, it's a level. And I guess when mathematicians were thinking of the name, they weren't feeling extremely creative that day. So they just called this level of infinity, the one that irrationals belongs to, Aleph One. Aleph One. So Aleph No, that's the cardinality of naturals, wholes, integers, and rationals. Aleph One, that's the cardinality of irrationals. What about reals? Well, real numbers is basically just all the rationals and irrationals put together. That's what the reals are. You're either rational or irrational if you're a real number. And we just discovered that the irrationals have a cardinality of Aleph One, which is greater than Aleph No. And remember, these aren't real numbers, these are levels. So part of the family of reals is at the level of Aleph One. Part of the family of reals is at the level of Aleph No. Since part of the family of reals is at the level of Aleph One, the cardinality of reals takes on that same cardinality, because part of it is uncountable. So we must state that the entire family of real numbers is also uncountable. So it's also Aleph One. What about imaginaries? Well, first of all, what makes a number imaginary? It's the square root of a negative real. A negative real. So, for example, square root of -2, square root of -1, square root of -pi, something like that. Those are all imaginary numbers. Well, if I'm allowed to put any negative real in the square root, and I know that real numbers are Aleph One to begin with, well, taking the square root of that Aleph One number, I mean, it doesn't change its level. It's going to be smaller, yes, but it doesn't change its level. It doesn't make it a smaller level. So the cardinality of imaginaries, since it contains real numbers inside of them, is also Aleph One. So we haven't found a third level of infinity yet. That doesn't mean they don't exist. And keep in mind that when I first started talking about power sets, and then I applied the power set rule, number of subsets, to infinite sets. We found that if you raise 2 to some infinite number, you get something bigger than that infinite number. And I could do that infinite number of times. Sorry. So that's 2 to the 2 to the 2 to the infinity. And that's going to be larger than the power before. So there are an infinite number of levels because I can keep doing this. But we're only going to discover 2 levels for this unit. Aleph null and Aleph One. Okay? Thank you very much. See you next time.